Now we study chapter 3, differentiation of functions of several variables. To define the differentiation and the derivative, we need to study limit first. So the first section, limit. So why we need to study limit? In the study of single variable calculus, we know that the derivative of a function, real value function, the derivative of this function at a point is the limit of the difference from the increment of the function divided by the change of the independent variable and take limit as x goes to x0. So this is the definition of derivative for single variable functions. So we need a limit. Of course, for our study of multi-variable functions, the situation is the same. So we study limit first. So here is the definition of limit. Suppose A is a set in Rn. Before define the limit, we need to define the so-called limit point of a set. Okay, so A is a subset of Rn. An element A in Rn is called a limit point of this set, capital A, if there is a sequence xk contained in A, but which is the point A removed, such that xk converges to A. I remind you that although here we denote A minus this point, remove this point, but if A is not contained in A, then A remove this point is unchanged, is the A itself. Okay, remember the difference of two sets is the set in the first set but not in the second set. Okay, so here A minus small a, if small a is not in A, then the difference is exactly A itself. Okay, so what this means? What is limit point? So a point is a limit point of a set if this set has a sequence not equal to this point. This means A is limit point means there is a sequence xk in A, but xk not equal to A, such that xk converges to A. Okay, so this is the same as we stated in the definition, that this sequence converge in capital A, remove the point small a. Okay, let's examine some example. Suppose A is the unit ball, removing the center, which is the origin. Okay, so this is our A, but the center is removed. Okay, then the center is a limit point. Of A. Okay, why it is the center? Because we can construct a sequence converging to this center from A minus the center. Okay, we take xk to be, for example, 1 over k, other coordinates are 0, then if k greater than 2, xk will be a point in A. Of course, A and xk is not the origin, therefore xk contained in this difference. And obviously, xk converge to 0, which is the origin. Therefore, by definition, the origin is a limit point of our set A. So this is a very simple example. So the limit point might not necessarily contained in the set A. Of course, limit point can also contain in A. If A is the unit ball without removing the center, then by the same argument, you will see that 0, the center, is also limit point of A. In this case, this limit point belongs to A. Okay. So in both cases, in our unit ball removing the center and which the center, in these two cases, all the limit point of A, in both cases, all limit point of A consist of the set. This set. How to denote this set? We write it actually, which is all the point in Rn. The norm is not greater than 1. That is the ball, but which the boundary sphere. In the first example, A is a unit sphere removing the center. In the second example, A is exactly the unit sphere. But in both cases, all the limit points of A are this set, A bar, consisting of all points which norm not greater than 1. Geometrically, this A bar is the closed ball. That is the unit ball which the boundary sphere. So this is A bar. Okay. So we still need another definition. All limit point. No, maybe. Okay. All limit point of A consisting of a set. We denote it by A prime. We call this the derivative set of A. Derivative. This is why we denote it by A prime, like the derivative of a single variable function. Okay. Now, having defined the limit point of a set, we can define the limit of multivariable functions. So this is a definition. Suppose A is a subset of Rn, and f is a function defined on A taking value from another Euclidean space Rm. Okay, and A is a limit point of our set A. So A is a limit point of capital A. We can simply denote this by A belongs to the derivative set of A, of capital A. Okay, so This means by definition, this means that there exists a sequence xk in A, but xk not equal to the point A, such that xk converges to A. We just define the limit point. So this is the meaning of limit point. Okay. So what's the limit of f? We want to define x converges to A, fx. We want to define this limit. What's this limit? Okay. This limit should be an element in the image of f in Rm, maybe not image, in the target Euclidean space. So L is an element of Rm. So if for any xk containing in this set, so that xk converges to A. So because A is a limit point of capital A, such a sequence xk exists. But of course, we can have many sequences has this property. If along all the such sequence, we always have fxk converge to L. So fxk is a sequence in Rm. L is an element in Rm. Therefore, we can say whether this sequence fxk converge to L or not. Okay. So if for any sequence converging to A, this is true, fxk converge to L, we say that the limit of f is L. Okay, so this is our definition of the limit of multivariable functions. Of course, in this definition, our multivariable function f can be a vector value function because it takes value in Rn, not necessarily R. If n is 1, so f is a real valued function. Okay, but we can talk about vector valued functions. Okay. So from this definition, we have a remark. So if A is a point, a limit point of capital A, and also A is a point of A, so A is the intersection of the derivative set and the set capital A itself. In this case, f is continuous at this point, if and only if the limit of fx when x goes to A is the value of f at this point. Okay, this is combine the definition of limit and the continuity of functions. We have this result. Here we require A to be in the intersection. Why? Because to define the limit, we need A to be a limit point. If A is not a limit point, for example, this is A, and our point small a is here. For x belongs to the definition of f, that is capital A, x could not goes to A. Okay. For x if this small a is not a limit point of this set capital A, those points in capital A could not converge to A, could not goes to A. Therefore, we could not say when x goes to A, what happened. So to define the limit, this is why we need to assume that A is a limit point of capital A. Okay. Now, the right hand side of this inequality, FA, only if A is an element in the domain of definition of F, namely capital A, can we say Fa. If A is not an element of the set capital A, the domain of definition, so Fa makes no sense. If this A is not an element of capital A. So, but if A is an limit point and also an element in A, then this makes sense and they are equal. Okay.